January 15th, 1919. Commercial Street, Boston, Massachusetts. At 12:40 p.m., a 50-foot tall steel tank containing 2.3 million gallons of molasses exploded without warning, releasing a wave of syrup traveling at 35 miles per hour through one of the most densely populated neighborhoods in America. 21 people died. 150 were injured. The disaster was not an accident. It was the inevitable result of corporate negligence, engineering incompetence, and a deliberate cover-up that began the moment construction started 2 years earlier. But to understand why this happened, you need to understand what molasses meant in 1917. The Purity Distilling Company needed molasses, vast quantities of it. During World War I, molasses was not just for food. It was a raw material for industrial alcohol, which was converted into munitions. Every gallon of rum-grade molasses could be distilled into ethanol, which was then processed into smokeless powder, TNT precursors, and other chemical weapons. The company's distillery in Cambridge required a constant supply, and the North End waterfront location was perfect for receiving shipments directly from the Caribbean by steamship. But there was a second reason for urgency. Prohibition was coming. The 18th Amendment had been proposed in December 1917 and was already gaining state ratifications. Purity Distilling knew that within 2 years, the legal production of drinking alcohol would be banned. Their business model was about to become illegal. They needed to process as much molasses as possible before the law changed, stockpiling industrial alcohol that could be sold legally for non-beverage purposes. This created enormous pressure to build fast and cut costs. The company hired Arthur Gell to oversee the tank construction in December 1915. Gell was not an engineer. He had no formal training in structural design, no background in metallurgy, no understanding of hydrostatic pressure calculations. He was a bookkeeper, a financial manager promoted beyond his competence because he was cheap, obedient, and willing to meet impossible deadlines. The actual design was drafted by Hammond Iron Works, a fabrication company in the business of making water towers and industrial tanks. But even those plans were never reviewed by an independent structural engineer. No one checked the math. No stress calculations were verified. No one asked a basic question. Will this hold 2.3 million gallons of liquid weighing 12 pounds per gallon? The steel plates arrived at the site in early 1916. Each plate was 1/2 inch thick, which sounds substantial until you understand the physics involved. A cylindrical tank 50 feet tall and 90 feet in diameter, when filled with molasses, exerts outward pressure exceeding 200,000 pounds per square foot at the base. For comparison, a modern water tower of similar size uses steel plates at least 1 inch thick, often thicker, with reinforcement rings every few feet to distribute the load. The Boston molasses tank had none of this. The plates were thin. The reinforcement was minimal. The engineering was non-existent. The rivets holding the plates together were equally inadequate. Workers hammered them into place without proper quality control or inspection. Many were cold riveted, meaning they were driven into the holes at room temperature rather than heated first. When metal cools, it contracts. Cold rivets shrink as they cool, creating stress concentrations and microfractures in the steel around the holes. Others were simply loose, inadequately tightened, allowing gaps between the plates. The tank was assembled in sections, plate by plate, row by row, climbing higher week by week. Workers later testified that the structure swayed visibly during construction, bending under its own weight before a single drop of molasses was added. One worker, John Maroney, told investigators that he refused to work on the upper sections because he believed the tank would collapse. He was fired. No water test was performed. This is absolutely critical. Standard engineering practice for any pressure vessel requires a hydrostatic test. You fill the structure with water, allow it to sit under full load for at least 24 hours, and inspect for leaks, deformation, or structural failure. Water is visible. Leaks are obvious. If the tank is going to fail, it will fail with water, which is harmless compared to molasses. Purity Distilling skipped this step entirely. Why? Because Arthur Gell knew the tank was already leaking. During construction, workers reported seepage between the plates. The first shipment of molasses arrived in December 1916, and within hours, the liquid began oozing through the seams. It seeped out slowly at first, thin trickles running down the sides of the tank, then more noticeably, then constantly. Residents of the North End complained. The neighborhood smelled like a candy factory. Children collected the dripping molasses in cups and jars, selling it or eating it. The streets were sticky. Gel's response was not to repair the tank. It was not to reinforce the structure, replace faulty rivets, or add additional support rings. His solution was to paint the entire tank dark brown. The logic was simple and sociopathic. If the tank is brown and molasses is brown, no one will notice the leaks. The company purchased industrial brown paint and coated the entire exterior. For 2 years, this worked. Visually, the tank continued to leak. The steel continued to groan under pressure. Every time a new shipment arrived, the structure expanded slightly, stressing the rivets further, widening the gaps between plates. Workers at the nearby freight yards heard popping sounds on a regular basis, sharp cracks like gunfire. Metal groaned audibly on warm days when the molasses expanded. The tank breathed like a living thing, bulging outward when full, contracting slightly when emptied. Engineers who visited the site after the disaster would describe it as a time bomb, a structure held together by inertia and luck, both finite resources. The final shipment arrived on January 12, 1919. The steamship Miliero docked at the Purity Wharf and pumped 550,000 gallons of molasses into the all-registrating tank, bringing the total volume to approximately 2.3 million gallons. The temperature that week had been unusually warm for Boston in January, reaching 40 degrees Fahrenheit during the day. This matters because molasses viscosity is temperature dependent. Cold molasses is nearly solid. Warm molasses flows easily. As the temperature rose, the molasses inside the tank became less viscous, which means it exerted greater hydrostatic pressure against the walls. The tank was now at maximum capacity, holding over 13,000 tons of liquid. The steel plates were bowing outward. Rivets were shearing. Workers heard the groaning intensify. No one stopped the operation. No one ordered an inspection. The company had war contract to fulfill and prohibition looming. On the morning of January 15th, the temperature rose even higher, reaching 43 degrees Fahrenheit. Inside the tank, the molasses warmed, thinned, and pushed harder against the weakened steel. The structure had reached its absolute limit, held together by nothing but momentum. At 12:40 p.m., momentum ran out. 12:40 p.m. The tank did not simply rupture. It exploded. Witnesses 3 blocks away described a sound like machine gun fire as hundreds of rivets sheared simultaneously, followed by a roar so loud it was heard across the harbor in Charlestown, 2 miles distant. The steel plates, each weighing between 2 and 5 tons, blew outward with enough kinetic energy to bend railroad tracks, sever a support column for the elevated train structure, and embed themselves in buildings across the street. The initial burst was catastrophic, but what followed was exponentially worse. 2.3 million gallons of molasses, suddenly released from containment, formed a wave 15 feet high at its peak, moving at 35 miles per hour. To understand the physics, you must understand that molasses is not water. Water has low viscosity, flows easily, and dissipates energy quickly when it spreads. A water wave loses height and speed rapidly as it moves away from the source. Molasses at 40 degrees Fahrenheit is a non-Newtonian fluid with viscosity approximately 100 times greater than water. It does not splash. It does not break apart into droplets. It moves as a coherent mass, a wall of liquid that carries debris, vehicles, and human beings with equal indifference. The density of molasses is roughly 12 pounds per gallon. The wave contained over 26 million pounds of fluid. The energy released was equivalent to a modern fuel air explosive. The wave struck the elevated railway support structure first, hitting beam number 34 with enough force to shear the steel column at its base. Engine number 318 of the Boston Elevated Railway was approaching the intersection of Commercial and Copp's Hill Terrace at that exact moment. The train operator, William White, saw the explosion and applied the emergency brakes. The train screeched to a halt 20 feet short of a section of track that no longer existed. The beam supporting the rails had been twisted 90 degrees, leaving the track suspended in midair above a sea of molasses. If the train had been 15 seconds earlier, traveling at normal speed, it would have plunged into the syrup below, killing everyone on board. White later testified that he saw the wave approaching and thought it was a brown wall, a solid object. He did not realize it was liquid until he saw buildings collapsing. The fire station at number 58 Commercial Street took the full impact. Firefighter George Leha was on the second floor when the wave hit. He described the sound as thunder, followed by the entire building lurching sideways. The brick walls on the ground floor shattered. Molasses poured through the windows and doors, filling the interior in seconds. Leha survived by climbing onto a desk, then onto a filing cabinet, then breaking through a second-story window and crawling onto the roof. His colleague, Nathaniel Bowering, was on the ground floor. Leha heard him shouting for help as the molasses rose. Then silence. Bowering's body was found 3 days later, embedded in hardened molasses near the rear wall of the station. His lungs were full of the sticky fluid. He had drowned standing upright, unable to move as the syrup filled his nose and mouth. The North End paving yard, directly across from the tank, was full of workers loading carts with paving stones. They saw the wave coming and ran. Some made it. Many did not. The molasses moved faster than a human can sprint, especially through debris. Antonio D.I. Stagio, a teamster, was thrown 60 feet by the initial blast and crushed against the side of a warehouse. His cart and horses were swept away, found later buried under 5 feet of molasses, both animals dead from asphyxiation. Maria D.I. Stagio, his wife, heard the explosion from their apartment 3 blocks away and ran toward the waterfront. She found her husband pinned beneath a collapsed wall, conscious but dying. He lived for 6 hours, long enough to tell her he loved her. Bridget Clufferty was inside her home at number 15 Cops Hill Terrace. She was 65 years old, bedridden from chronic illness. The wave collapsed the front wall of her house, and molasses poured into the ground floor. Her son Michael tried to reach her, but was driven back by the rising tide of syrup. Neighbors formed a human chain, passing ropes and planks, trying to create a path through the molasses. They reached her 4 hours later. She was alive but unconscious, her airway coated with molasses. She died in Massachusetts General Hospital that evening from asphyxiation and internal injuries caused by debris. The physics of drowning in molasses is nightmarish in ways that water drowning is not. When a person inhales water, the lungs fill rapidly, oxygen exchange stops, and unconsciousness occurs within 2 to 3 minutes. Death follows shortly after. Molasses is different. It is too viscous to fully enter the alveoli on inhalation, but it coats the trachea and bronchi, creating a barrier that prevents oxygen from reaching the lungs. The victim remains conscious, struggling to breathe, feeling themselves suffocate slowly. The molasses also adheres to skin and clothing, making movement nearly impossible. Victims describe the sensation as being trapped in cement that hardens as you struggle. The more you move, the more exhausted you become, until you simply cannot move anymore. Rescue effort began immediately, but were hampered by the molasses itself. The Boston Fire Department arrived within minutes, bringing hoses and pumps. They sprayed seawater on the molasses, attempting to wash it away. This did nothing. Molasses does not dissolve in cold water. It mixes slowly, forming a brown emulsion that is even harder to remove than pure molasses. Firefighters waded into the syrup and became stuck themselves. Volunteers formed chains, grabbing arms and legs of victims and pulling. Many rescued became trapped and had to be pulled out by others. Sailors from the lightship Nantucket, docked at a nearby wharf, used ropes and planks to reach victims in the deeper sections. One sailor, John Berry, crawled across a makeshift bridge of debris to reach a child trapped under a collapsed market stall. The child survived with a broken arm and severe lacerations. Berry's hands were raw and bleeding from the abrasive mixture of molasses, sand, shattered glass, and splinters. The harbor itself turned brown. Molasses flowed downhill, following the natural slope of Commercial Street toward the waterfront, pouring into basements, flooding the freight tunnels beneath the street, and spreading across the surface of Boston Harbor. Ships docked at the piers were coated in syrup up to their waterlines. The smell was overwhelming, a sickly sweet odor that permeated clothing, hair, and lungs. For weeks afterward, residents tracked molasses through the streets of Boston. Sidewalks remained sticky through the summer. The final death toll was 21. The injured numbered 150, many with permanent disabilities. 8 of the dead were children. The youngest victim was 10-year-old Pasquale Ian Tosca, who had been playing near the tank when it exploded. His body was recovered 2 weeks later, found beneath the wreckage of a collapsed warehouse. The molasses had preserved his body perfectly, preventing decomposition, freezing him in the moment of death. His eyes were open. The Purity Distilling Company's first response was not remorse. It was not an apology. It was a lie. Within hours of the disaster, company representatives began spreading the story that the explosion was caused by sabotage, specifically by Italian anarchists opposed to American involvement in World War I. They claimed that a bomb had been planted inside the tank and detonated remotely. This narrative was deliberate, calculated, and politically convenient. The year 1919 was the height of the first Red Scare. Labor strikes were spreading across the United States. Anarchist bombings had occurred in several cities, including a bomb mailed to Attorney General A. Mitchell Palmer. The public was primed to believe that radicals were responsible for any industrial disaster, especially in immigrant neighborhoods like Boston's North End. The theory was absurd from the beginning. No evidence of explosives was ever found. Investigators combing through the wreckage found no trace of detonation residue, no blast pattern consistent with a bomb, no fragments of timing devices or wiring. The steel plates had failed from internal pressure, not external force. The rivets had sheared from tensile stress, not from shock waves. Metallurgists examined the fractured steel under microscopes and found stress fractures consistent with prolonged fatigue, not sudden explosive force. But the company repeated the claim relentlessly in newspapers, knowing that the accusation alone would muddy the legal waters and shift public perception. The lawsuits began immediately. 119 plaintiffs, representing victims and their families, filed claims against Purity Distilling and its parent company, United States Industrial Alcohol. The lead attorney for the plaintiffs was Damon Hall, a prominent Boston trial lawyer who understood that this case would set legal precedent that would reverberate for decades. Until 1919, corporations were rarely held liable for industrial disasters. The prevailing legal doctrine was caveat emptor, let the buyer beware. If a worker was injured, it was considered part of the inherent risk of employment. If a structure failed, it was deemed an act of God, an unforeseeable accident. Hall argued something revolutionary. He argued that companies have a legal duty to ensure their structures are safe, that engineering negligence is a form of corporate liability, and that failure to follow accepted engineering practices constitutes gross negligence equivalent to criminal recklessness. The trial began in 1920 and lasted 3 years, becoming the longest and most complex civil lawsuit in Massachusetts history up to that point. The proceedings generated 4,000 to 5,000 pages of testimony, thousands of photographs, engineering diagrams, metallurgical reports, and expert analyses. Auditor Hugh Ogden was appointed by the court to hear the evidence and deliver findings of fact. Engineers testified about proper design standards for pressure vessels. Metallurgists examined the steel composition and found it contained excessive sulfur, making it brittle. Structural analysts calculated the stress loads a tank would have experienced and demonstrated that the design was inadequate by a factor of 3. The evidence was overwhelming and damning. The tank had been fatally flawed from the moment the first plate was riveted into place. Arthur Gell, the man who oversaw construction, was called to testify. Under cross-examination by Damon Hall, Gell admitted he had never studied engineering. He admitted he had no training in structural mechanics. He admitted he knew the tank was leaking from the day it was filled. He admitted he ordered it painted brown specifically to hide the leaks from public view. He admitted that no hydrostatic test was ever performed, despite this being standard industry practice. His testimony was devastating and self-incriminating. One exchange is preserved verbatim in the court record and has been cited in engineering ethics courses ever since. Hall asked, "Mr. Gell, did you believe the tank was safe when you authorized it to be filled?" Gell answered, "I believed it was adequate for the purpose it was designed for." Hall replied, "I did not ask if it was adequate. I asked if you believed it was safe." Gell paused, then said, "I believed it would hold." Hall pressed, "That is not the same as safe, is it?" Gell did not answer. The judge ordered him to respond. Gell finally said, "I suppose not." The defense attempted repeatedly to resurrect the anarchist bombing theory, calling witnesses who claimed to have heard a loud bang immediately before the collapse, suggesting an explosion separate from the structural failure. Engineers for the plaintiffs systematically demolished this argument. They demonstrated through acoustic analysis that the sound witnesses described was consistent with rivets failing in rapid succession, creating a cascading failure that sounded like firecrackers or gunfire. They showed that the steel plates had buckled outward, not inward. proving conclusively that pressure originated inside the tank. They presented evidence that the steel was substandard, the rivets were improperly installed, the design lacked adequate safety factors, and the entire project was rushed to completion without proper oversight. In April 1925, after nearly 5 years of litigation, Auditor Hugh Ogden delivered his ruling. He found that the collapse was caused entirely by structural failure due to improper design, substandard materials, and negligent construction practices. He found Purity Distilling Company and United States Industrial Alcohol jointly and severally liable for all damages. The companies were ordered to pay $628,000 in damages to the plaintiffs, equivalent to over $10 million in today's currency. More importantly, the ruling established legal precedent that transformed American engineering and construction law. For the first time, courts held that companies could not simply build structures as cheaply as possible and claim ignorance when they failed. Engineers were now professionally liable for their designs. Companies were required to follow accepted standards of practice. Structures had to be tested before being put into service. The concept of due diligence entered the legal lexicon. The impact on engineering practice was immediate and profound. States began requiring that all major construction projects be overseen by licensed professional engineers who could be held personally liable for failures. Pressure vessels, storage tanks, and industrial structures had to undergo hydrostatic testing and regular inspections. Building codes were revised nationwide to include mandatory safety factors, stress calculations, and material specifications. The Boston Building Department created new inspection protocols and hired structural engineers to review plans before construction permits were issued. The disaster also exposed the human cost of corporate negligence in ways that could not be ignored. The victims were mostly immigrants, working-class families from Boston's North End, people with no political power and no voice in city affairs. They were invisible until they were dead. The trial gave them a voice. The testimony of survivors, the presentation of evidence, the graphic descriptions of suffering, and the indisputable proof of corporate malfeasance forced American society to acknowledge that workers and residents deserve protection from preventable disasters. This was a turning point in labor law and public safety regulation. The site of the tank remained a visible scar on the Boston waterfront for years. The wreckage was cleared, the bodies recovered, the debris hauled away, but the ground itself was stained brown. On hot summer days, decades later, residents claimed they could still smell molasses rising from pavement. The elevated railway was repaired. The fire station was rebuilt. Life continued, but the memory persisted, passed down through generations. In 1983, the Boston Historical Society installed a small plaque near the site. It reads, "On January 15, 1919, a molasses tank at this site exploded under pressure, killing 21 persons. Several nearby buildings were also demolished and many others were damaged. The plaque is easy to miss, mounted low on a wall near a parking lot. But the story is impossible to forget. The Boston molasses disaster remains one of the most bizarre and tragic industrial accidents in American history. It was not caused by bad luck, unforeseeable circumstances, or an act of God. It was caused by a company that valued profit over safety, by a man who painted a tank brown to hide its fatal flaws, and by a system that allowed such negligence to continue until people died. 21 people, 8 of them children. That is the cost of cutting corners. That is the legacy of Arthur Gell and Purity Distilling. And that is why, to this day, engineering students study this disaster as a fundamental lesson in what happens when hubris meets physics. The tank was painted brown. The leaks were hidden. The warnings were ignored. And 21 people paid the price.